Good. Thanks for coming. Thanks for coming to my breakout session. So this one, I'm 10 breakout sessions. This ridiculous conference. You have chosen wisely. You made the right choice. It's going to be the best one, I promise. Maybe I'll just dance around for a minute or two as people might be filtering in. I'm glad it's the first day. First day energy is always the best energy. Well, what's going on? There's so much to see. Everybody's still open-minded, you know. You haven't heard the same pitch 75 times yet. Meet your old friends. Post-lunch, first day energy. Is this SynBioBeta veterans in the room? Are there a lot of SynBioBeta veterans? There's just one? Just one? Wow. Amazing. Oh, two more. I'm a long time SynBioBeta fan. First time speaker ever. I've always been a big fan of SynBioBeta. I think it's very powerful. I think something that John Cumbers saw early on about synthetic biology is that there's a real need in this ecosystem to get aligned or to mediate between these very complex capabilities that we have in synthetic biology and the products that people actually want, the products that people actually make. So my first experience at SynBioBeta was 10 years ago, looking at it as an academic, as the place where it's like, oh, that's what people want. That's what people want. It's not actually differential equations that you go and sell out in the real world. So that was my, and so John saw that early on, and I think it's very powerful. I think the most impactful thing that we can do as an ecosystem at this conference is to get aligned, to get organized around the way that we think about these very complex things that we're doing and how we're translating those technologies into the world. Because we really, almost the whole ecosystem is here, right? So if we have the right conversation about how we do that, we're going to go and it's going to spread, it's going to take over the world, and we can be aligned in the way that we think about these very complicated products that we're bringing to market. So my name is Jake. Introduce myself. I work at Ginkgo Bioworks, and I think this idea of translating between what are our capabilities and what does the market need, I think it's the most exciting. I think it's the most interesting thing in synthetic biology right now. And it's something that I think about at Ginkgo Bioworks pretty much full time, where my title is called Developer Evangelist. Developer Evangelist. It's how do we take these complicated products, how do we make them accessible to developers? And this is a challenge that platform companies, for example, in tech, take very seriously. They take this idea very seriously. So in tech, there actually is a job called Developer Evangelist, and it's not a made-up job. It's not a made-up job title. In tech, if you have a platform like a Microsoft Windows or an Amazon Web Services or an Unreal Engine in gaming, and you want people to build products on top of your platform, you have people with the title of Developer Evangelist whose job is to go out, figure out what the developers need, and give them the resources that they need in order to be able to use those very complicated products effectively, right? And they take it incredibly seriously. If you go to the Amazon Web Services website right now, right, there are hundreds of hours of free online courses that you can take. There's documentation, there's white papers, there's meetups, there's Discord servers, there's developer communities, there's this incredibly rich pile of resources that are helping people make use of this platform technology, right? So this is something where we are quite far behind tech in order, and I think one of the major reasons is that we are not really aligned in terms of our thinking around how we manage all of the complexity in our products. So I think it's going to be a big unlock for the synthetic biology ecosystem if we can create together a sort of shared framework for organizing complexity. So this is the right forum to have that conversation. And now is the right time to have this conversation because the complexity in synthetic biology technology has reached a breaking point. It has reached an absolute breaking point, right? This is a meme that I made for Twitter in 2022. I chose, so 2012 for me is an inflection point. Okay, this was when CRISPR rolled out in a big way, 2012. Before 2012, it was possible for one or a small team of experts in synthetic biology to have real visibility on all of the tools that were available for use in the ecosystem, right? It was always a team effort. Didn't mean that you were doing everything yourself, but it was possible to be aware of all of the synthetic biology tools that were available for your use if you were going to go and you were going to use those to build a particular product. That was really true. That I know that, right? Because I was working with those tools in 2012. 2022 is when I came to Ginkgo. It is my full-time job to understand Ginkgo's technical capabilities so that I can communicate them. I've been doing it for 18 months, right? And I am not fucking close to being able to understand Ginkgo's capabilities. And I'm falling further behind every day because we are adding more capabilities faster than I can understand. So this is the state of the synthetic biology ecosystem today, is we need a new framework for managing that complexity. Right? So we need to bring it into a place where no, we're not going to know everything that synthetic biology can do anymore. But nevertheless, we need to be able to use it and deploy it. So I'm not going to tease you. I think I have an answer. Just kidding. But I think that this is the right place to start the conversation, and I'm going to start the conversation by, I'm going to propose an answer. I'm going to have a thesis about how this works. Okay? So, first question is, what makes developing in the Foundry era different from developing in the pre-Foundry era? How is 2022 different from 2012? And I think the answer is that scale is transformative. It is qualitatively transformative. So, which is to say that it's not just more of the same thing. It becomes a different thing when the automation gets big enough, when the data sets get big enough, when the sheer number of capabilities that you have at your disposal gets big enough. You've transformed the problem, and you're now thinking about a qualitatively different kind of problem. What is the right way to make SynBio capabilities accessible to developers? My proposal for that is services. We're going to think about services as an abstraction layer that makes the scale of synthetic biology accessible. So it's an abstraction layer in the sense that it's going to let a developer make use of services effectively while freeing them from the need to know every detail, every piece of complexity of the problem that they're working with. So it's going to be services as an abstraction layer. How does it work? How does this look in practice? How will this look in practice? I have a couple of case studies of recent Ginkgo projects, and well, I don't know. We'll see if we have time. Maybe we can sort of invent our own case study. I have some ideas about strawberries. So I'm very excited to bring these kind of ideas. A little bit nervous to bring these kind of ideas to SynBioBeta, because it's not like I invented the problem of complexity, right? Complexity is at the very center of the idea of synthetic biology as an engineering discipline, right? It's that people have strong opinions about complexity in this community, right? So you get a little nervous when you want to talk about complexity. And so I think it's important to think about it as a conversation. I think it's important to just note that this is going to be only one of many strategies about managing complexity. And in particular, I want to nod to this classical framework for how we think about complexity in synthetic biology. Can I do a vibe check here? How many people have seen this figure before? Is this familiar?
We saw something similar.
Something similar?
Yeah, and the intro 101 thing yesterday.
And the intro 101 thing? Okay. It was probably the same one. It's quite okay. Fair enough. Okay, I see some people nodding. So this is from Ron Weiss. Ron Weiss's lab, who was a panelist this morning. 2006. Laying out this idea of layers of abstraction as a tool for managing the complexity of synthetic biology. And I don't know if this was the first articulation of this particular model, but I do think it's one of the most famous. This is what inspired me to become a synthetic biologist, because it's a very beautiful framework, right? So the analogy here is to the layers of abstraction that we use particularly in computer hardware. So here on the left, this is how computer hardware is built up. You've got your transistors. The transistors are assembled into logic gates, the logic gates into computers, the computers into networks, and so on. And because each of these are separated by layers of abstraction, it makes it possible for someone who is working on, say, networking software to be able to do that without having to know every detail about every transistor in every computer which they could. So obviously, that was good idea, tech, good job, yes, computers, good, that worked, right? We steal that, we're gonna try to steal that all the time. Maybe biology could work the same way. So maybe in this vision, it's proteins and genes are the bottom layer, and they become more abstract. Proteins and genes are abstracted into pathways into cells into tissues, and so on. So when I was preparing this talk, I was thinking I'm going to come in here and be like, we're throwing it out. We're throwing out this framework. This is old news. We don't do this, right? But now, I don't know. That's a little too takey. That's a little too hot takey. It actually is pretty good. It's actually pretty good. It's contributed a lot to it. So I don't want to say that it's wrong, but I do have two criticisms. So the first is, if you've been in this field as long as I have, you have heard it 8,000 times. Yeah, but isn't that biology doesn't actually work that way? Biology is not really modular like this, right? And it's true, right? We didn't build biology. We didn't engineer it like computers. So we didn't get to say, okay, here's the breakpoint where two chips can talk to each other. There's crosstalk in biology. But in biology, there's crosstalk across the layers. There just is. There just is, right? So you can modify one gene, and if it's the right gene, you can have a massive, massive impact at the tissue level, right? That's the whole premise of gene therapy, right? It's either that works. So just from a technical perspective, there's always been this like nagging thing about, well, maybe that's not really how biological complexity is organized. There are some cases where that works very well. There's some places where it works quite poorly. My second complaint about this physical framework is that it has tended to over-index synthetic biologists on the physical devices that they're building and not on the problems that they're solving. Okay? So I work in marketing now. Anybody do marketing? Anybody do marketing? Yeah, right. So so we have this thing in marketing. I haven't been doing it that long. I read a few books, sort of know how it works. Okay, there's this thing. This a breakthrough idea in marketing is that you pay attention to what your customer wants, and then you do that thing. Okay, that's the one. That's the big marketing thing. But in the context in synthetic biology, the version of that is you had right at the inception of the field, we had a bunch of like people who really loved skateboard engineering, right? And they were like, no, we need to only talk about the trucks. We just need to talk about trucks all day long, and if we just get the trucks right, people are going to buy these trucks. Right? But the reality is we need to focus a little bit more on the problems that we're solving. Has anyone know what this is? I'm doing a real history of synthetic biology. This is making me feel old. Anybody recognize this?
Restriction enzymes?
They're restriction enzymes. They are. That's good. Yeah. There's an NEB restriction enzyme. I guess I can't ask for more than that because you can't read what they say. Right? So that's not really fair. But this is a little piece of synthetic biology history. This is a biobrick assembly kit. This is a biobrick assembly kit, which was important enough that it's now in a freaking museum in Wales, New South Wales, Australia. This is probably 2008 or 2010 era. So that the idea here was that synthetic biology was going to be driven by DNA assembly. Okay, so that's what biobrick assembly enabled. You could take different biological parts. Here's a promoter. Here's a coding sequence. Here's a terminator. Use a kit like this to mix and match them to build out a bigger piece of DNA, a physical piece of DNA. And then so that was going to be your baseline abstraction layer. Then you assemble that up into a bigger piece of DNA, and that's the next abstraction layer, and then a bigger one, and maybe that lets you do tissue engineering, right? And so that was the thesis. It was these physical parts of DNA, which were going to be how we organize the ecosystem. And what happened, inevitably, what happened, as we all know now, total DNA synthesis just came and made this obsolete. You didn't have to do biobrick assembly anymore because you could buy assembled DNA assembled through any number of other technologies, right? And that's ongoing now in bigger fragments and so on. And so the lesson here is that, right, people didn't want biobricks. People didn't want biobricks. They wanted functional DNA, right? That was the problem that needed to be solved. And so the framework that we use for managing complexity should be robust to this evolution that can happen in the back end of our technology, right? So if I say I'm gonna, here's how I offer DNA, for example, to the developers today, I want to do it in such a way that next year when there's an amazing breakthrough in DNA assembly, I don't have to completely rethink everything about how I structure my. So I think there's a solution for this, or at least there's a framework for this that's very useful. It comes from the software world as well, because we have to steal everything from software all the time. Is the API. So an API is a different kind of abstraction layer, this time for services. API is an abstraction layer for services. So it is divided between a front end, which is for the user. This is where the user puts in their needs for a particular service, scoped within what is technically possible to deliver, right? So this is where you put in your call, you put in the parameters of whatever is the thing that you need, and then you have the back end. That's the execution layer. The job of the back end is to deliver the solution, deliver the service to a customer. So probably a familiar framework to a lot of people. What I like about it in the context of synthetic biology is that it allows the back end to be all about execution. So your nerds can just live in the back end, right? They can do whatever they want. They can solve the problem however they need to solve it, as long as they're delivering what the API calls for. And if the technology advances in the back end, that's great. People working on the front end, they don't have to see it. They don't have to care, right? That frees up headspace for them to do whatever they're doing, right? The product that they're building using this particular API. So it's liberating for people who live on the front end. I also like this model because it allows the front end to be all about the customer, to be all about the customer's needs, right? So this brings the problem of product development, if you like, right, of serving a real need directly into the technical framework of how do we manage the technical complexity. Because that's the whole point of the front end is to deliver a thing that somebody wants, right? If you build a front end and nobody wants to use it, then you haven't built a useful service. So, I think it's pretty powerful. So this is how I am today thinking about what we do at Ginkgo. How we are managing the complexity and how we put all of our Foundry capabilities in front of the developers, in front of the users, and the public, and making them accessible. And so I want to go through some sort of case studies, right, or just some examples from Ginkgo of how this kind of service-focused complexity management is working for getting more synthetic biology services out into the market. So this is from our pitch deck, and this is like by the numbers, the scale of Ginkgo, right? So there's just a bunch of numbers that show you how Foundry is very big. We have lots of sweet capabilities, right? So there's also what's in it, right? So we're the biggest user of synthetic DNA in the world. There's hundreds of scientists. There's 3.8 billion gene sequences in our database. We've got all these cool robotic work cells. We do millions of strain tests annually. It's awesome. It is awesome. Okay, and it sometimes will get your foot in the door, right? So people come and they visit the Foundry. They're like, whoa, this is really cool to look at, right? I am excited by all this technology and automation happening at scale. So it does sometimes get your foot in the door, right? But scale like this, it doesn't sell to customers. Customers don't give a shit. Right? You don't go to Amazon Web Services because you're impressed by how many servers they have. Okay? You want to know, can they solve your problem? We're living it, right? Here we are, right? I think a lot of people in synthetic biology ecosystem have some version of this problem where they're like, we have this awesome capability, and then I go out and I want to make it available. People want to use it, and they don't really understand what's in it for them, right? Or they don't know how to. I'm not getting the expert users that I dream of, that are just going to read my mind and use me perfectly. Yeah. So the surface framework takes all of those capabilities, puts that scale. That's in the back end. Okay, so the front end, what the customer sees is enzyme services, microbe services, cell therapy services, AAV engineering, RNA therapeutics. These are just a few of we've been doing a lot of this sort of technology showcase webinar events, and so we do the way that we're sort of structuring our offering, right? So it's like, okay, well, here's what can you get in for binder engineering, right? So there's one of binder engineering services. What can you get if you're doing some gene therapy, you want to engineer a capsid? Okay, well, what do I want to do? I need to engineer my payload because I want some central nervous system specific promoters. Okay. So the kind of services framework. All of these have, like, of course, they have technical constraints, right? Technical inputs and outputs, right? That's like what the API section of this looks like, right? It's sort of framing what is possible, right? You can't get everything from every service, right? There's a sort of a framework that turns these services into things that we can actually execute on. But what I want to sort of highlight is the commercial value, or the way that this sort of services framework can take the commercial value of scale, which is cool, but probably not something that the customer is really thinking about, right? And make it into an actual value proposition. Make it into something that the customer is thinking about by sort of moving it into the front end of the API. And so this is what the customers want at the front end of the API. So it's this de-risking of a particular capability. Right? So this the number one thing that customers want is they want biology to work. They just want it to work. So a lot of us are very good at synthetic biology. We believe that we know what we're doing. We are very capable. We have lots of very cool technologies. Take them, put them in front of customers, and say, this is definitely going to work. And they like, no. They don't. Right? Because it's bio's hard tech. Bio's hard tech, and nothing works, right? Nothing ever works, right? Or at least for a certain type of personality, if you like, right? There's a lot of skepticism, right? So scale is a tool for us that allows us to de-risk execution on the back end, right? Basically, we've done a lot of these projects, so we have a good sense for whether or not they're going to work. We can bring that into the front end by saying, okay, so now you're just going to pay for success. You're only going to pay for success, right? So this is a very much a non-technical part of the API, right? Like, this is not a DNA assembly feature of the API. This is a customer-focused feature of the API. We're not asking them to worry about how the mechanism, all the complex reasons why scale enables better execution in synthetic biology. We're just offering them what they want on the front end through this very product focused. How much time do I have? Do I have time for a few more case studies? 15 minutes? How are people doing? How are people feeling about this? Did I get it right? Get it right? Services? And we're going to go and use services to manage complexity. Yeah, I'll do a couple more case studies. These are more on the technical side for how this sort of works in practice for projects. How sort of Foundry scale thinking changes the way that these particular projects can be framed. Okay, so this is a metabolic engineering project that we did recently for a partner called Braskem, Brazilian company. They had a metabolic engineering problem. They wanted to make a chemical called monoethylene glycol. And they wanted to make it from sugarcane bagasse, right? So pretty like classic metabolic engineering problem. They had come to this problem already And they had done some rational engineering on this strain. But it had a few problems, right? So there's some classic metabolic engineering problem. There's this dioxic shift issue that you get, right? So in bagasse, it breaks up into xylose and glucose. And if you're working in E. coli really wants to keep the glucose, and it wants to ignore the xylose, right? Classic. Let's jump my note. The 1960s. Classic dioxic shift problem. So you've got it, but the xylose is what makes the product, right? So there's this dioxic shift issue, and then just classical metabolic engineering, right? We need a lot more of the products in this pathway that are going to produce this their output. So you could approach this problem, this metabolic engineering problem, from a sort of from a DNA assembly point of view, right, or from a physical assembly point of view. You could say, okay, what am I going to do? I'm going to engineer a bunch of enzymes that I need. I'm going to put them together into a pathway. I'm going to express them all on a really high level, and I'm going to solve this like a metabolic engineering problem. So you absolutely you could approach it that way, right? You could say, okay, I'm going to build up my complex systems from simpler DNA components. But I think this is a great example of the fact that they wanted an outcome, right? They don't care how they get it, right? They don't care. You don't need to do like it. You could if beautiful synthetic biology is going to get you there, then they're happy with that. But you don't have to do that. So in this case, there's an alternative solution. So we used a new tech that we've onboarded for adaptive laboratory evolution. And so this is great for exactly this kind of problem. So you have a particular feedstock that you need, you want to adapt a bacteria so that they're particularly good at growing in a particular feedstock. So evolution loves to solve problems like that. So you grow them continuously, feeding them this feedstock for many, many, many generations. Let evolution work, and you get a strain that is particularly good at this feedstock, right? So in this case, it wasn't building a bunch of gene circuits. That wasn't the answer. Adaptive evolution is a new technology that has been on the Foundry for about 2 years. Solves this problem on the back end. One of many different ways that you could potentially solve this problem. A service that is offered to a customer who doesn't necessarily care how the problem is going to be solved. Okay, so I think it's a kind of an elegant example of how using this service framework lets you it gives you clarity on the front end for what needs to be built, while giving you flexibility on the back end for how you actually solve the problem. And in this case, it was adaptive laboratory evolution. So, similar example. This is a peptide ingredient. So this is a nutrition project. So they had a particular strain. Strain was secreting a peptide product. They wanted a lot more of it. Also could be done with conventional synthetic biology. Also was done, in this case, with a particularly weird new technology called NCAPS for encapsulation of strain. So what we did was mutagenize the strain, huge numbers, 200,000 different variants, random mutagenesis, encapsulate them in these little microcompartments, right, in these nanoliter scale reactors, develop an assay for the secretion of this peptide that is working in these nanoliter scale reactors, and then screen them in huge numbers on this NCAPS machine just to find the random naturally occurring variants that are secreting this protein in high quantities. Right? This machine blew my mind. I had absolutely no idea that this kind of technology could exist. Right? If someone had come to me a few years ago and said, okay, you're a synthetic biologist, solve this problem, I would not have even have known that this type of tool was in the toolbox. right? And just the sheer scale of what you can do, 200,000 variants in these nanoliter scale reactors, is it's surpassing, right? It's a completely new way of delivering on this particular need for enhanced protein secretion. And then the sort of subtext for both of these projects, which is that these customers, for different reasons, they didn't want targeted genetic modifications. So they wanted a non-GMO solution for their particular problems. Right? So that was a constraint on the front end, on the API for these particular technologies. So that's what I have to say. So I think services. I think the service layer with an API is the right metaphor for thinking about the ways that we manage complexity in synthetic biology. I want to hear what you think. So I think that we as a community need a shared framework, a shared notation, a common language for the way that we talk about complexity in synthetic biology and the way that we make that complexity available to our customers and to our developers. Because I think that if we get aligned on that, I think that's going to be the next level of unlock for this ecosystem, and it's going to keep that next level of complexity from getting too out of control.